So the final speaker today is Tom Hutchcroft. Tom is a grad student at UBC. You should hire him if you can. He is the winner of the Outstanding Graduate Student Research Award at UBC a year ago, and particularly strong case because he wasn't graduating. There's prejudice against him, but still he won it. So Tom's does many things. He's going to talk to us about geometry of high-dimensional spanning forests.
Thank you, Ed, and thanks to the organizers for inviting me. So I'm going to be talking about the strange geometry of high-dimensional spanning forests. So this is joint work with Yuval, which I did when I was an intern here this summer. And before I start, perhaps I should mention the title of my talk is a homage to Joel Spencer's book, The Strange Logic of Random Graphs. And if you're aware with some of the work in this area, basically what I'm going to be doing here is I'm going to be taking that theory that's for sort of Erdős-Rényi graphs and sort of redeveloping it, but in a much more sort of difficult setting where there's a lot of dependence and there's also a lot of spatial structure. Okay, so let's start with the basics. So I'm going to be talking about uniform spanning forests. But before I tell you what those are, I need to tell you what a uniform spanning tree is. Well, if I have a graph, then a spanning tree, it's very simple. It's just a connected subgraph that contains every vertex, and it's a tree, so it doesn't have any cycles. Okay, and a forest is just a tree, but without the connectivity assumption. Okay, and given a finite graph, a finite connected graph, there's some finite set of spanning trees, and the uniform spanning tree is just, well, I just choose one uniformly at random, right? So here is an example. This picture, I think, is due to maybe David, or it's Oded's, okay. And so this is a uniform spanning tree in white of a 30 by 30 box in the square grid. Okay. So it turns out, this might seem like it's a very simple thing, but in fact, it has a ton of connections to loads of other things in probability. So here's a long list. I added rotor routers, which I was missing out on, but obviously after Lionel's talk, I had to add this. But so I don't really want to go into any of this, but I hope that many of you will be able to find some topic you're interested in this list. And okay, very good. Okay, but I'm not talking about uniform spanning trees. I'm talking about uniform spanning forests. And now, this is a rather misleading name because the one thing that a uniform spanning forest is not is a uniform spanning forest. That would be too easy. No, instead, what they really are their limits of uniform spanning trees in infinite graphs. Okay, so if I have an infinite graph, now I have an infinite set of spanning trees, possibly, so I can't just choose one uniformly at random. I need to take some kind of limit. Okay, and this was first done by Robin Pimantel back in 1991, following a suggestion of Russ Lyons, I might add. And so these are, as I said, defined as limits of uniform spanning trees on large finite subgraphs. Okay, so let's just define this properly because it's going to be important. So if we have some infinite graph G, and I want to assume it's locally finite, so that means, although the graph is infinite, the degree of every vertex, the number of edges incident to it, is finite. Okay, and if I have such a graph, I can take an exhaustion of it, by which I just mean an increasing sequence of finite sets of vertices whose union is the entire set of vertices. Okay, and I have the sequence, and for every n, I'll let Gn be the induced subgraph, the subgraph of G induced by Vn, which just means the graph that has vertex set Vn and it has an edge if and only if that edge comes from the original graph and both of its endpoints are in the set. Okay, now you can also do something that might seem a bit strange. So for each n, we'll also form this graph G star n by, instead of taking the induced subgraph, we'll take everything outside of our vertex set Vn and contract it down to a single point. So here you can see this on the right here. So here you can imagine I have like the infinite grid. Here I have this induced subgraph on the left, and on the right, I have this contracted thing. Okay. And now we have, it turns out in general, there are two ways to define the uniform spanning forests with these two different sets of boundary conditions. So the free uniform spanning forest is the limit of the uniform spanning trees on the induced graphs, whereas the wired uniform spanning forest is the weak limit of the uniform spanning trees on this graph where I squish the boundary down to a point. Now, both limits were shown to exist by P. Mantel in this 91 paper, and in particular, they don't depend on how we chose to exhaust our graph. Okay. Now, actually, in this talk, I'm mostly going to be interested in sort of Euclidean settings, ZD, so the hypercubic lattice. And in this case, actually, the boundary conditions don't matter. So the two limits give us the same object. And this is actually true in any amenable transitive graph, more generally. OK. Now, sort of the first sort of interesting thing that was proven, or one of the first main interesting things that was proven about this model, is that although in every stage, when we're taking this limit, we have a tree, the limit might not be connected. That's why we have to call it a forest. So, in fact, what P. Mantel proved in his 91 paper is that, and Lionel mentioned earlier in his talk, is that the uniform spanning forest of the d-dimensional lattice is connected, i.e. is just one tree rather than a forest, if and only if the dimension is at most 4. Okay, so you might think, well, why? That's a good question. So why is dimension 4 important? Well, it turns out we can understand this quite well thanks to an algorithm for sampling the uniform spanning forest due to David, which actually was not available to Robin P. Mantel when he proved this originally, but it makes it much clearer why it's true. So as I said, so David introduced this algorithm that basically lets us build the uniform spanning tree out of what are called loop-raised random walks. And I should say David did it for finite graphs, and then it was generalized to sample the wired uniform spanning forest of infinite transient graphs. The extension to recurrent graphs is rather obvious, but the transient case was done by Benjamini, Lyons, Peres, and Schramm in this big paper in 2001 where they proved many, many things. We'll see some of them shortly. Okay, so what's the idea of this? Well, before I can tell you what Wilson's algorithm is, I have to tell you what a loop-raised random walk is. So if we have some path in a graph, we define the loop erasure by erasing loops chronologically as they're created. So you think we sort of trace the path out, and whenever we close a loop, we delete it, and then just get this smaller path without the loop, and then we carry on taking the same steps, delete the loops. So formally, it's this sequence of times, and it's not so important to read this, but this is the definition. And if we take a loop erasure of a simple random walk, it's what's called loop-raised random walk, and it was this has been studied very thoroughly now, originally by Greg Lawler in 1980. Okay, so what does Wilson's algorithm do? Well, I'll tell you how it works in the infinite case, and then I'll show you a nice simulation, not by me, in the finite case. So we have an infinite transient graph, and what I need to do to start with is enumerate all the vertices in just some arbitrary order. It doesn't matter. And we can define a sequence of forests in the graph as follows. So firstly, well, let's set F0 to be the empty forest. It's not very interesting. It has no edges or vertices. Okay, now given whatever we've generated up to time I, we start a random walk at vi plus 1, so sort of the next vertex in the queue. And this random walk is going to be independent of everything we've done so far. And we stop this random walk if and when it hits the set of vertices that are already included in the piece of the forest that we've generated so far. Right? So if it never hits this set, we just run it forever. Okay? And then what we do is we take the loop erasure of this stopped random walk path, and we take the fi plus 1 to be the union of the forest we generated so far, plus this path. Okay? And the amazing fact is that if you do this forever until you've taken the union, you've generated a spanning forest. The fact that it's a spanning forest is obvious, right? But in fact, it's actually sort of a uniform spanning forest, even, which is, when you first see this, I think it's kind of crazy, right? I mean, you can do these things in any order you like, etc. Okay, and I actually have a simulation of this on a box. So this is the finite case. I should say this is done by a guy called Mike Bostock, who is an amateur spanning tree enthusiast and former graphics editor for the New York Times. So he has many different implementations of Wilson's algorithm. So here you can see this is the purple loop arrays path and it's trying to find the bit of the tree that's already been generated. And as soon as it finds it, it's just going to stick on. And this is one that's been done already. I made sure it doesn't take too long. I gave this talk once before, and I did a live thing, and it took about 5 minutes. If he'd done the wired boundary conditions, it would be much faster, but I guess you wouldn't see so much. But you can go on his website. You can run fresh simulations for yourself. OK. So when we run this algorithm, we think about whether we're going to get connectivity or not. We get a sort of, more or less for free, a criterion, which is, well, when we're running this algorithm, when do we start a new tree? Well, it's exactly when we run one of these walks and it never hits the set of vertices that we've already included. Okay, so in particular, we find that this wide uniform spanning forest is connected if and only if a random walk must intersect an independent loop-arraysed random walk. Okay, so this already tells us a lot. Now, it turns out, there's a nice paper by Lyons, Peres, and Schramm, where, in fact, a random walk hitting a loop-arraysed random walk is about as difficult as just hitting a simple random walk. So there's this factor 2 to the minus 8, but otherwise it's a constant, so who cares? So this gives us a really nice criterion, which appeared in this paper, that the wide uniform spanning forest of a graph is connected almost surely if and only if two independent simple random walks on the graph intersect almost surely. And it's worth noting here, it's sort of obvious if you think about it for a moment, that if you take two independent random walks, then intersecting almost surely is the same as intersecting infinitely many times almost surely. So I guess just to clarify, by intersection, I mean if you look at the sets of vertices that they visit, then that has intersection. They don't have to intersect at the same time or anything. Okay, and once you have this, it's pretty easy to get back P. Mantel's result, which again, this technology was not available to him at the time. So, for example, just to give you a flavor, I mean, if you want to calculate the expected number of times that two random walks intersect in ZD, it's really easy because you take this sum, right? If you decompose according to where they intersect, let's say they both start at 0, and at what time they intersect, so you're doing this sum here over n and v, and if you sum over v, you just get this sum of the, and you do some time reversal, you get n, sorry, they don't have to hit at the same time, do n and k. Then you do some simple algebra and you find that you get this sum of n times the probability that you've returned to 0 at time n. And we know that this return probability is about n to the minus d over 2. And you do your integration or your p-series, and you find that the expected number of intersections is infinite if and only if d is less than 4, less than or equal to 4. And then it's not so hard, you do second moments and you get this theorem. So I guess this fact about random walks goes back to Erdős and Taylor in 1960 or something. Okay, so really the starting point, sorry, I'll get rid of this virus thing. The starting point for what I really want to tell you about today is the following sort of amazing thing that was discovered by Benjamini, Keston, Peres, and Schramm. The paper was published in 2004. So they found that this disconnectivity transition that happens in 4 dimensions is just the first of a sort of an infinite family of transitions that occur every 4 dimensions. Okay, so I want to show you a cartoon to see what I mean by this. Okay, so for d less than or equal to 4, there's only one tree in the forest. Okay, that's good. Now, for d greater than or equal to 5, there are infinitely many trees in the forest. Okay, so far, nothing new. However, it turns out that if the dimension is between 5 and 8, then every tree in the forest touches every other tree almost surely. So what I mean by that is there's some edge of the lattice here, so for any two trees, I can find some edge of the lattice which has one tree on one side and the other tree on the other. So they all touch. So although it's disconnected in a kind of a very mild way. Okay, now this holds for dimensions between 5 and 8, but it turns out that for dimensions greater than or equal to 9, this is no longer true. However, if D is between 9 and 12, then for every two trees, I can find a third tree which sort of communicates between them. So the tree on the left, for any two trees I pick on the left and the right, I can find a third tree that sits in the middle and touches both trees. And this is true if and only if D is between 9 and 12. Okay. For D bigger than 13, that's no longer true. But now, if D is between 13 and 16, I can find a chain of two trees that intermediate. So I can connect from here to here to here in 3 jumps. Okay, and basically what happens is that this pattern continues. So every time the dimension increases by 4, you need one more tree to communicate between two arbitrary trees. Yes?
Are these chains of trees unique?
No, there'll be infinitely many of them, actually, when, yeah. Okay, so that's what I just said. Okay, so this is a pretty crazy thing, right? I mean, I don't really know of any sort of precedent for a result like this. Maybe Yuval does, but, well, to me it was pretty crazy. So what we wanted to do is we want to say, well, is this the whole story? And it turns out it's not. So in fact, if you look at some more things that are rather similar to what I was just talking about, you can actually find sort of qualitative changes to the way the uniform spanning forest is connected that occur every dimension once it's not a tree anymore. So as soon as you get above 5, there are things you can look at that really change every single dimension, not just every 4 dimensions. Okay, so at least for dimensions bigger than 9, we can phrase a formal version of this result in terms of what we call ubiquitous subgraphs in the component graph. And that goes back to the book I was mentioning of Joel Spencer, really studies ubiquitous subgraphs in Erdős-Rényi graphs. And then the D between 5 and 8 is a bit more subtle, but we'll see it later. Okay, so let me give you an example of what I mean by one of these things that changes. So this is going to distinguish between dimensions 10 and 11, which are bang in the middle of one of these intervals of length 4. Okay, so suppose we take 3 trees now. So what we prove is that if D is less than or equal to 10, we can always find a 4th tree that touches all 3 trees. Okay, so they're sort of all communicated to by this master tree. Anyway, that's no longer true in higher dimensions. Okay, so that already gives us something to separate between 10 and 11. Now, what if we try the same thing with 4 trees? Well, it turns out that now the threshold is 9 dimensions. Actually, really the critical dimension for this particular thing is somewhere between 9 and 10. It's fractional, but it will happen in 9 dimensions and not in higher. So we can always find this 4th tree that touches all 4 of them. And in fact, in 9 dimensions, we can also do this with 5 trees, but not with 6. 5 is the most you can do in 9 dimensions. So every 5 trees, there'll be some tree which touches all of them somewhere. Okay. So, well, let's try and think about these things in a slightly more principled way. How are we going to generalize this to find things to separate all dimensions? Okay. So what we can do is we can define something we call the component graph. So this is very simple. It's just going to be a graph where now the vertices of the graph are the trees in the uniform spanning forest, and there's an edge between them if they touch somewhere, right? Okay, so it's very simple. And more generally, you can also sort of draw an edge if they just come close, and turns out it doesn't really change anything. Okay, and so we can rephrase this BKPS theorem as saying that the diameter of the component graph increases by 1 every time the dimension increases by 4. So in particular, this means the component graph is very simple in low dimensions. So dimensions 1 through 4, it's the most simple graph of all. It's a point. And then in dimensions 5 through 8, it's a complete graph with countably many vertices. Okay, so it's worth mentioning, I mean, it's kind of obvious, but these component graphs have infinite degrees. So you realize when you work with these things that certainly, in my experience, I never work with graphs with infinite degrees, right? And you realize basically nothing you know about graphs is true anymore. And anyway. So, okay. So, what we really wanted to do is say, what can we say about these graphs other than the diameter? Right? That was really the starting point. Okay, so now I can tell you about these ubiquitous subgraphs that you've heard so much about. So we start by saying a graph with a boundary is just a graph with some distinguished set of boundary vertices, partial V. Okay, and then the interior vertices are the remaining ones. Okay, so suppose we have a graph G, which will be our component graph, and we have a graph with boundary H, and we have some set of vertices of G that are indexed by the boundary vertices. Okay, then we say that this graph H is present at this collection of points if I can find some vertices in G indexed by the interior vertices of H, so that I see the combinatorics of H that I'm expecting to see. So XU will be connected to XV in G if U and V are connected in H. Okay? And we say, are adjacent in it, rather than connected. Okay? And we say that H is faithfully present if we can do this in like an injective way, so that all these points that we choose are different.
Do you require the connectivity among the boundary vertices to match H?
Yeah, sure. In what we're doing, it's sort of, we can never enforce that to happen, so it doesn't really matter whether you do it or not. But yeah, sure. You do require it. Okay, and now we say that H is ubiquitous in G. Well, what's ubiquitous mean? It means it's everywhere, right? So it just means it's present at every X that's indexed by the boundary vertices. And we'll say that it's faithfully ubiquitous if it's faithfully present at every X. So, okay, so maybe this definition is a bit weird, so let me give you some examples. Okay, so the most simple thing is just the diameter. So if you have a path of length n, and you make the boundary vertices like the ends of the path, right, obviously, then it's ubiquitous if and only if G has diameter at most n, right? It just means for every 2 points, you can find these points in the middle so that you see the combinatorics of the path. And it's faithfully ubiquitous if every 2 vertices in the graph can be connected by a simple path of length n. Okay? In particular, we never require sort of non-edges to be there. We don't mind those. Okay, and this thing I was telling you about before with this, 3 things connected by something else, these are just asking whether stars are ubiquitous. So, if I have an n star, then it's ubiquitous. It just means that every set of n vertices have some common neighbor. Okay, so here's our theorem. So at least for dimensions bigger than or equal to 9. Okay, so the first thing is, so what I'm interested in is, given a finite graph with boundary H, is it or is it not ubiquitous in the component graph? And the first thing is that only the bare essentials of the geometry of ZD affect whether it's there or not. So in particular, if I have this distance R component graph, or even I change to like a different group of polynomial growth with the same dimension, it doesn't change which finite graphs with boundary are ubiquitous in the component graph. So it just depends on the dimension. Okay? And the second thing is monotonicity. So if you have 2 dimensions, this D1 bigger than D2, then any finite graph with boundary that's ubiquitous in the component graph in the larger dimension will also be ubiquitous in the smaller dimension, right? So in smaller dimensions, it's easier to have more stuff. Okay? And then we have that we can separate dimensions. So for every finite graph, there exists a finite graph with boundary that separates between any 2 dimensions. So I can always find one that's ubiquitous in one dimension, not in the other. Obviously, this can only hold for dimensions bigger than 9, because everything's just a complete graph below then, or a point. Okay, and moreover, if I give you some finite graph with boundary h, you really can compute the threshold for when it does or doesn't occur. There's a fairly simple expression. Okay. So.
Why does it have to be 9 and not 8?
Well, it could be 8, yeah. Sure. Yeah, it's kind of trivial in the, yes, yeah. Okay, so you might think, well, you know, how would you prove such a thing? Well, it still comes down to, you know, mostly pretty elementary stuff. It's a lot of computation that you churn through. And then at the end, you have to apply some sort of abstract nonsense, some 0-1 laws. Okay, so, you know, it's a classic probability argument. So, okay. So firstly, to show non-ubiquity, it sort of suffices to do first moment stuff. So what we can do is we can take some points and we want to know, you know, is this graph H going to be present there or not? So we can look at the number of sort of these connection points that witness that graph being there. So we can look at the number of points. So for example, say I have these 3 points here, here, and here, and I want to know, are there trees, do they have this 3-star present there? And so what I can do is I can look at the number of edges of ZD that witness this in the sense that, you know, one choice would be to take this, this, and this, right? I see those edges and I see that they're all connected in a tree here, and they're all connected to each thing respectively, and that gives me like a witness. And similarly, I could take this, this, and this because these two play the same role. I can choose either one. I'll say more about this soon. Okay, so to show like non-ubiquity in high dimensions, we basically want to show that, you know, we don't have these things in expectation if we start with faraway points, and so, you know, we don't have them. We have a positive probability not to have them. Okay, so showing that something is ubiquitous in lower dimensions is a bit more involved. So first we have to sort of lower bound first moments, then upper bound second moments, you know, use the second moment method. That's only going to get us so far though, because basically what we'll do is we'll look at shells and we'll find that in each sort of dyadic shell, we have a constant probability of seeing one of these sort of witnessing configurations. And that means that we have a positive probability, you know, by Fatou's lemma of seeing infinitely many witnessing configurations like this. But it turns out that's enough because we can get a 0-1 law for whether this happens or not. So we know that the probability is positive, we can boost it up to 1. Okay, and the relevant 0-1 law is related to what's called indistinguishability of the trees. Okay, so, sorry, what time am I supposed to finish by?
So I think we started a little late, so maybe 13, 14 after.
Okay. All right, so I'll probably have to go, I'll skip all the calculations, which you don't want to see anyway because it's 5 o'clock. Okay, so basically, the main point is that we know how to compute connection probabilities for uniform spanning forests in ZD. And it all comes down to this quantity called the spread. So if we have a finite set of vertices, so here's sort of the real definition. It's the inf of the product over the distances where we look at distances in some abstract tree with that vertex set. Okay, so in fact, the only reason we use this definition is because it's really a definition. In practice, I mean, if you just want to estimate this thing up to constants, which is what we always do, you pick a enumeration of the set, and you take this product where you look at ui, and you look at the closest uj in the set that's where j is less than I, and you just multiply up all those distances. Okay? And it turns out that if you have a set of vertices in ZD and you want to know what's the probability that they're all in the same tree at the uniform spanning forest, it's up to constants, it's the spread to the power d minus 4. And this 4 that's here is the reason why you see 4 so much in, in the theorem of Benjamini, Keston, Peres, and Schramm, and so forth. Okay, and moreover, if you take a bunch of different sets and you want each set to have one tree that contains it all, but you want the trees to be different, then the probability that that happens is bounded by just the product of the probabilities for each set. And sort of in practice, when we have like reasonable sets, there's going to be a matching lower bound. I mean, there are obvious obstructions to this in general.
Different i's, you mean different wi's?
Yeah. Yes. Yeah. So yeah. Okay. Right. So, and the way you prove this is using Wilson's algorithm. Okay. Now, if you want to estimate these first moments, so you'll look at the number of sort of witnessing configurations in some dyadic shell, say. So they're between 2 to the k and 2 to the k plus 1 from the origin. And suppose all these points are much closer to the origin. Right? And if you try and estimate the first moment, so here's a proper definition of this witnessing thing. Okay. So, and here's some more examples, but I'm going to have to go through these quickly. So here's an example of sort of witnessing configurations for this graph with boundary where the white vertices are in the boundary. Okay, so if we want to compute the probability that some particular configuration of points is a witness, then it's very easy using that expression I just told you. So we just have to take the spreads. So for each vertex of the graph H, we're going to have a tree that we want to be there. So we need to have sort of one term for each vertex of H, and the boundary ones are going to include this fixed point in the spread, but the interior ones are just going to have edges. Okay, and so we have this expression. If we want to calculate the first moment, we need to sum this over all collections. Now, your first guess, you want to estimate this thing, and it's not crazy, but it's complicated to estimate. So you want to sort of identify where are the main contributions to this sum coming from. So your first guess might be, well, most points in an annulus, if I pick a sort of a uniform list of k points, they're all going to be about the same distance, right? About maximal distance. So you might start by guessing that all the distances are going to be on that scale, right? And if you do this, you'll find that, they're about, if we're on this dyadic shell between 2 to the k and 2k plus 1, there's about 2 to the d times the number of edges times k such configurations, and they all have this weight 2 to the minus d minus 4 2e minus the number of interior things. Okay? So you multiply these together and you find that this is the contribution roughly of these kind of configurations, right? So our first guess, if we're just doing things with the first moment and taking this very crude approximation, indeed this really was our first guess, that h is going to be faithfully ubiquitous if and only if this exponent is positive, right? Because if it's negative, then the expected number of things is going to decay. And indeed, this gives the right answer to a path. This agrees with what we saw earlier. You have to check it. But in fact, in general, it's not true. And the reason why is, in fact, the real contribution to first moments is going to be something like this. So if we take some graph like this, where we have like a complete graph and then attach just two boundary things on the sides, what we're going to want to do is have this edge here, this connection points, these two are going to be well spaced, and then all this big cluster of connection points is all going to kind of happen in a small area of constant size. Okay, so in general, sort of optimal things that are really contributing to the moment are going to have some clumps of points that are at constant distance, and the rest are going to be basically at maximal distance. And there's a nice way to interpret this in terms of hypergraphs. So, what's a hypergraph? Well, it's just a graph except edges can connect more than two vertices. Okay, and we define hypergraphs with boundaries just as before. And if we have a graph, and we have some equivalence relation on the edges, then we can, union each equivalence class and get a hypergraph, which we call a coarsening. So here, for example, we might take all the edges in this complete graph and just union them into one big hyperedge. Right? And you can see how this would happen before, because if we have this configuration of points and some of them are clumped together, and the clumps are at maximal distance, we can use this to define one of these coarsenings. And the upshot is that you can express the contribution of this thing in terms of a quantity that's computed from the hypergraph. Okay. And so basically, if you want to calculate the first moments, you have to do an optimization over all the coarsenings you can do. So you find all these hypergraphs. Okay. And so in the end, we have this quantity eta bar of the graph H, where we take these expressions, where this delta is the sum of the degrees of all the vertices in the hypergraph. And we take the maximum over all coarsenings. And the real first moment is going to be like 2 to the power of that times k. So, and this was just sort of the main contribution, but it turns out it's really the real first moment up to a sort of a lower order thing. Okay, and so this first moment test is going to tell us that we get something as ubiquitous. Our guess would be that it's going to be ubiquitous if and only if this quantity eta bar d of h is non-negative. Okay, so in fact this isn't quite true. So it is true that if it's negative, then you have these exponentially decaying first moments, and you're not going to get anything. However, we want to do some second moments, so really we'd want that in the other case we get that the second moments are like comparable to the first moment squared. But in fact, this doesn't always happen, but it's the only reason it can't happen is a kind of obvious obstruction, and it turns out it's the only one. So
Obvious in retrospect.
it's obvious in retrospect. No, I mean this really was obvious. The thing about the coarsenings was not obvious to us for a long time, but this we knew because this happens in Erdős-Rényi graphs. Okay, so one problem is if something's faithfully ubiquitous, then also its subgraphs have to be, right? But this quantity eta d, you might find that say I have a graph like this, then this dense bit over here is much harder to build than I then have this long path which is really easy to make. Right, so this long path is going to cause the first moment to blow up, even though this graph obviously can't be there because of this dense part. But in fact, this is the only obstruction. So provided that you have that this quantity eta d of h prime is positive for every subgraph, then in fact that turns out to be the right criterion. So maybe I'll just quickly skip ahead to this. So, here's the theorem is that you can compute exactly whether or not the thing is ubiquitous or not just by, we have this quantity eta d, which unfortunately I had to go through quite quickly, so you probably don't remember what it is, but it's a very simple thing. And you have to, do this sort of min-max thing where you look at coarsenings of subgraphs, and if that's non-negative, then the graph will be faithfully ubiquitous. And if you want this weaker thing, which is ubiquity, then you have to see whether there's a quotient that's ubiquitous. And right. So okay. So I'll skip out the bit about the 0-1 laws, unfortunately, but just tell you about how do you separate 5, 6, 7, 8. Well, okay, so in this range of dimensions, the component graph was not interesting, right? It was just a complete graph. However, all this stuff I've been telling you about hypergraphs should perhaps convince you maybe we should be looking at hypergraphs instead. So what you can define is you take some R, and you can define a component hypergraph by letting a set of trees have a hyperedge connecting them, if and only if there's some ball of radius r that all the trees intersect. Right? So this defines the component hypergraph. And now this has some non-trivial structure even in these low dimensions. Okay, and basically everything I've said so far applies equally well to hypergraphs as it did to graphs. So we get exactly the same criterion. And so let's see how we can separate dimensions 5, 6, 7, 8. Well, it's these pictures I had at the start. So separating 5 from 6 is very easy. You just take this hypergraph on the left, which is just one big edge with 5 vertices. Okay? So what this means is that in 5 dimensions, every 5 trees of the uniform spanning forest, there's some ball of constant size that they all have to intersect, right? And 5 is the most you can do, it turns out. So if you try and do this with 6, you will not succeed in general. In 6 dimensions, this is no longer true. You can still do it with 3 trees. So every 3 trees in the 6-dimensional spanning forest will intersect some ball of constant size. Okay, and separating between 7 and 8, this is the nicest hypergraph we could find. It's not so nice. Well, it's simple, but writing it down what ubiquity this means as a sentence is not simple. Anyway. Thank you.
So we have time for a couple of questions for Tom.
Is there anything separating 1, 2, 3, 4?
I mean, in those dimensions, we have sort of the more traditional, shall we say, things that we look for in statistical mechanics. I mean, the critical exponents of things are going. You need to look at more quantitative things, right? I mean, so one of the interesting things about this is that, normally we have this mean field behavior in high dimensions, right? High dimensions are not interesting. Everything stabilizes and exponents are the same. But here we really keep seeing changes in high dimensions.
But let me give another answer, is that you can build this similar theory or try to build it with other objects instead of the uniform spanning tree, like with random walk paths or interlacement paths. And Tom has done some of that.
Right. Well, actually, it's not so clear what to do here. Somehow, in the BKPS paper, the results they could get were much more general. So sort of as long as you knew how the connection probabilities decayed, and you had some second moment estimate for the same thing, that was basically all you needed. So you can do the same thing with other models. But here we really have this thing with the spread, and that's just not true for other things. So it seems like the theory would be rather different if for like interlacements or something.
So look at it positively. It's a non-trivial extension is needed.
Maybe another alternative answer. So if instead of generating the trees by a simple random walk, you use a long-range random walk, then you have a continuous version of this changes the dimension continuously. Mm-hmm. And in particular, you can get multiple trees also even in 1 dimension. And probably you're leaving this for some student to.
I mean, I think, yeah. I mean, it's sort of it's exactly, you do all the same calculations except you put an extra parameter everywhere.
Then you have criticality. Sometimes you have fractional dimensions.
Yeah. I mean, there is some.
It makes sense to do that.
Yeah.
Suppose instead of ZD, I had some other group of polynomial growth with the same volume growth. Can you distinguish between those?
Yes. So between that and ZD, not by these things. So all these things are exactly the same. Only the dimension matters.
But we say that's not a bug; it's a feature because universality holds.
Right. Yeah, exactly.
So you can't tell if you're in Z4 on Heisenberg and you consider this good.
Exactly.
Yeah.
If I have 2 graphs of infinite degree and something is ubiquitous in one, if and only if it's ubiquitous in the other, are they isomorphic?
No. That's a good question. So actually, the real reason why I started this project is that I'd done this work on indistinguishability with Asaf, and we wrongly believed that it implied the component graph was transitive, right? Because we had this theorem that says all the components look the same, and transitive means every vertex looks the same. But this is where things that you can only say in quotes, maybe you shouldn't be saying at all.
Can we quote you on that?
it turns out this deduction fails for measurability reasons. It's a bit like saying because a Bernoulli sequence is ergodic, so it means two samples look the same up to a shift. Oh, they must actually be shifts of each other. So the graphs themselves are genuinely random. So talking about whether they're isomorphic or not it's not so meaningful.
If there's no more questions, join me in thanking both Tom and Sebastian